All right. So last class, what you've seen with Jesus was what? Refresh me on that. You were right. You were going to see co-integration and pairs trading. You finished up on pitfalls. Was that it? I think it was time series pitfalls where you last saw what you last saw with Jesus. Not today, yesterday. Yeah, awesome. You've seen Animal with me as well. And you've seen something about unit root as well. So today, what we go and see, yeah, a lot of tests. We're going to see a lot of tests as well. Don't miss it too much. Okay. Let me share my screen. So this class will be a lot of speaking, a lot of storytelling, a lot of back and forth between you guys and me in order to understand what we're doing, because this is a new topic that we're applying to the syllabus. Okay. Let me share our studio. Okay, so imagine, and this example you probably heard on your econometrics 1 class. Imagine that you see two drunks, okay, two drunk people, a lot of alcohol going through their veins, and they are wandering around, stumbling upon, I don't know, walls, the street, maybe into itself, and the drunks, they don't know each other, okay? So what you can gather of what I can tell you is, one, the two drunks are basically random walks, okay? And since they don't know each other, they're independent. There's no meaningful relationship in between their paths. They're completely random in between them. 100% independent, okay? Now imagine instead that you don't have two drunks, okay? Imagine instead that you have one drunk, but that one drunk is walking a dog, okay, with a leash, okay? So this time there is a connection, right? The drunk is holding the leash towards the dog, and thus, what is the nature of this connection? So notice that even though the drunk has an unpredictable path, because the drunk is holding a leash towards the dog, then the dog's path can be predicted, the drunk's path. Okay, so given the location of either the dog or the drunk, we have a pretty good idea of where the other might be, or the distance in between both of them. Okay, so that margin, that distance is fairly predictable. So imagine the dog wanders too far away from the owner. Okay, so if the dog wanders too far away from the owner, it will tend to come back to the owner. Why? Because the leash has a finite length, right? So the dog should come back to the owner. Two, it shouldn't try to lose him, right? The dog should avoid losing his owner or her owner. Okay? So the two should stay closely together, despite a tendency to wander around on their own. Because again, speaking, we're treating a drunk. So its path is a random walk. Now we describe this kind of relationship by saying that the drunk and the dog form a co-integrated pair. Okay, so if we will do it in more econometric and technical terms, if we have two non-stationary time series, okay, so if we have two non-stationary time series, let's say X and Y, that these become stationary when different. What does that mean? Remember, for example, if when we're talking about prices. Now, prices are not stationary, but when you take the first difference and then you resell it, so you get the return, then that is usually stationary, weak stationary, right? Then these become stationary when differenced. Okay. Now, what is this called? A non-stationary time series that becomes stationary. This is called I0. I1, I mean. I1, and it turns into I0 when stationary. So this is called a 1 series. This one is for integration. Okay. One example, the easiest one, the random walk, right? So, so for example, let's imagine that we have one linear combination of x and y. Okay. Now, if we have one linear combination of x and y that is stationary, we say that they are cointegrated. Linear combination is stationary, they are cointegrated. So cointegrated, and the stationary means that it's I0. Put this one into LaTeX format as well. Does that mean that it becomes pretty like this? Let's just put our notes together while we do this. Okay. So in other words, neither x nor y walk alone. They walk kind of together, right? They hover around a constant value. There is some combination. So let me rephrase myself. X and Y on their own, they don't really go anywhere, right? But their combination does. So we can think as cointegration as, for example, describing a particular long-run equilibrium relationship in between two series. Now, you can have a cointegration of more than two series, but right now for the topic, we're going to see with just two, okay? So, examples. Uh, yes, that is correct, Omar. Examples. One example is, for example, income and consumption, okay? How does this work? If your income increases, then your consumption increases. If your income decreases, then consumption decreases. Right? That's pretty straightforward. For example, the story of a book and a movie adaptation, said book. Now, I was going to talk about Ready Player One, but most of you probably haven't seen that movie. Let's talk about, I don't know, Harry Potter. Now, it is really common for people to read at least one Harry Potter, and most of you have seen the movies, I imagine. Now, one can tell that the movie adaptation and the book are not exactly the same, right? But by knowing one, you have an idea what's going to happen or what's happening on the other one, right? They might differ in small details, but the overall plot is the same. Another general example, the number of patients that enter or leave the hospital. If you have people leaving the hospital, then there's a space for new people in the hospital, so the number of people entering the hospital might be related to the number of people leaving. Okay? Any questions so far, guys? Okay. So why do we care about this? Why do we care about co-integration? So especially in our topic, so quantitative finance, co-integration is used to form the basis of a pair's trading strategy. Okay. So suppose let's do this in finance. So suppose that that again we have X and Y, but X and Y are stocks. Okay. We have it. we have X and Y stocks. Okay. And they are co-integrated. Okay. We can say, for example, that they are co-integrated in a relationship such as X, for example, minus 2Y is equal to Z. Okay, where what is Z or Z, whatever you want to call it. Now Z is the stationary linear combination of these two stocks. Remember, it's stationary. That is very important. Okay. Now imagine, for example, let's put an example. Okay, example. Set X is McDonald's. Let's say X is Coca-Cola, and Y is Pepsi. Okay? Pretty pretty similar businesses. If you if we if you would go too much like inside the company, you would see that Pepsi has a lot of ad spending and ad revenue that's different than Coca-Cola, but just as a product, they are pretty similar. Okay. So what does that mean? So if Pepsi and Coca-Cola are related, such as Pepsi minus 2, no, Coca-Cola minus 2 Pepsi is a linear stationary relationship, then you would then you would then you would say that if okay, then you would say that X, so Coca-Cola usually is priced twice as high as Pepsi. Okay, so by following the the relationship Coca-Cola priced twice as high Pepsi. Okay, so we expect Coca-Cola to move down and Pepsi to move what? Half down? No. Yeah. So imagine, let me write it down. Imagine that Coca-Cola, yeah, Coca-Cola priced more than twice Pepsi. How do you expect Pepsi to move? I mean, how do you expect Coca-Cola to move? Or Pepsi, you know. So the usual relationship is that Coca-Cola should be priced twice as high as Pepsi. Right now, Coca-Cola is priced more than twice as high as Pepsi. How do you expect Coca-Cola to move? Should Coca-Cola move up? Should Coca-Cola move down? Exactly, right? So either Coca-Cola should go down or Pepsi should go up to revert to the usual relationship, right? So usually in pairs trading, what we set is a threshold. Okay, so imagine that, for example, you can follow this trading strategy. X what was it? Minus 2y. If x minus 2y is greater than a threshold, then if the threshold is positive, then greater than 1, what do we do? What do we do with Coca-Cola and Pepsi? No. If these, let's not put it greater than 0, okay? Greater than, because it can be different than 0. Usually to give you a little bit of a range in order to trade at, and not to put 1,000 orders at the same time. So no, what we should do is we should sell X, so in this case sell Coca-Cola, and buy Pepsi. Why? Because the positive relationship that is applying X to this relation is too high. So we need to lower X should be lower, and thus reduce this amount in order to diminish this relationship. Okay? Then the other thing with Pepsi is the same, right? If Y is too high, then this number is getting higher, right? Smaller, I mean. So we should buy Pepsi because it should go up in price. So likewise, if you're a thing around, so instead of minus this one, and D is greater than one threshold that doesn't change, then what should we do? Oh, so threshold is like a little bit of space that you give yourself. So if you put it at 0, then once that target hits, you're going to throw a million of orders at the market in order to keep it around there, right? If you make it small enough, so it's like an epsilon in math. If you put it small enough, then you don't have to. You can make 1 or 2 orders, and that's it. So a threshold is a space that you put in between two values. In this case, we're using it for a small space that you put in between two values. What was the other part of the question? Sorry, I forgot. Chris, can I explain again? Sure. So imagine that, let's put it in values, okay? Imagine that you have Coca-Cola at 35, Pepsi at I don't know, 15. Now, your relationship said that Coca-Cola is priced twice as high as Pepsi, right? So the price of Coca-Cola, which is 35, minus 2 times the price of Pepsi, usually you a Z, that's a zero mean stationary process. However, right now, you're not getting 0, you're getting 5. What does that mean? Either this should go down or this should go up, or both. Okay? And Coca-Cola should go to 30. Okay? Should go to 70.5, or something in between. Okay? So if the if a not if the contrary thing happens, then you buy Coca-Cola and sell Pepsi. Hopefully that's clear. Awesome. All right. So there are a lot of different tests, okay, for this kind of stuff. So how do you detect cointegration? So a really easy method that only works, however, with two variables is the Angel and Granger test. Okay, so and I'm not going to develop all of the tests. I'm going to mention them. So how does the Angel and Granger work? So let me put it in bullets. So one, you have to check, and we've kind of mentioned already this process. You have to check that X and Y, put it in order to determine that they are actually time series. Let's put it in like this. X and Y are I1. What was I1? Can you guys remember? What was I1, guys? You have to do one difference for them to be stationary, right? Then estimate co-integrating relationship. So what is the co-integrated relationship? Basically, YT is equal to any not constant uh, coefficient, that's the word I was searching for. Yeah, coefficient. Yeah, I forgot the word, sorry. XT, your error, right? Let's put an epsilon. T. Okay. And how do you do it? Just a simple OS. Now, what you have to check is check that the co-integrating residuals, so epsilon t, are stationary. And how do you check that? By using a unit root test. And we're going to develop this concept. Usually the most famous one is the augmented Dickey-Fuller one. Okay. Now, something else I should mention over here is error correction models. Uh, correction models. Sometimes you have a relationship with your cointer variables that have error correction mechanisms. So for example, let's say that we have again the xt and yt. So xt might be an alpha of yt. So far, it's basically the same, right? The thing is that we have to expand upon this. Because remember that what we've seen already from time series is that we can do some autoregressive representations of our variables, right? So imagine that this is not just yt. This can be xt minus 1 plus, I just put alpha 1 and alpha 2, okay? I don't want to put beta because we're going to talk about a different kind of beta later. Alpha 2, yt minus 1. That's your error, right? So let's say that this one has mu t. Another model that works really similar, but instead of x, it is y. Instead of alpha, let's do theta. Not right, theta. There you go. Yt. That's true. Xt. And instead of mu, let's say that this is v. So you have these two models. Now there is something called the Granger representation, and this is where the beta comes in. Okay, Granger represent them as, just copy this out. No, grab it bit by piece. What does the Granger representation tell you? The Granger representation tells you how to actually find that disequilibrium. So remember, we said that the cointegration is a long-run equilibrium relationship. But it is really important to find the disequilibrium that can come in between sometimes, because the world is not always in equilibrium. Like Keynes actually said that. So before the efficient market hypothesis actually came around, Keynes said that there is no real equilibrium. Like the greatest lie we tell ourselves in economics is that we think everything in equilibrium. Alvaro.
Yes, I was going to mention something about Keynes. In my class of economic one, no, economía financiera, we talk that
Uh-huh.
the equilibrium is the exception, and also that Keynes said that unemployment in the in the decade of 1920 was so
Uh-huh.
long that you could consider that an equilibrium.
Exactly.
Mhm. Yeah, good.
Yeah. Who do you have as a teacher?
Eh, Gonzalo Adulto, no, no mentira. Ah, Rolando Luna, Rolando Luna.
Orlando is a great teacher. He actually was my
Your teacher?
thesis. I forgot the word. It's not judge. The judge are the people that judge you. I don't know, guys. It's late. But he helped me make my thesis. So he's definitely the best teacher for that course.
What was your job?
But
Your boss at your job?
what was my job? What?
No, it was your boss, you said?
No, no, no. He helped me with my thesis,
Thesis? What is a thesis?
my undergraduate thesis. In order to graduate, you have to present a thesis. Yeah,
Ah, sorry. Yeah, I listened to another thing. Yeah, okay, okay.
yeah.
Thank you. Yeah.
No, he's really good. If anyone wants to take financial economics, definitely go with Orlando, 100%. So where was I? So yeah, the the cointegration relationship is is basically what tells you the long run equilibrium. However, in most moments we're not in the equilibrium. We're pathing towards the equilibrium. So we're in a disequilibrium moment. And because we're in this equilibrium moment, we have to measure how that disequilibrium works. The Granger representation allows us to do this. Okay, so the change xt be represented as, let me use another letter over here. I'm not gonna use a letter. I'm gonna change this one to something else. G, G. Okay. So now I can use alpha again. Okay, so alpha 1 by the difference of, and this is not correct, this is like this, the other variable that's co-integrated minus, and this is where the beta comes in, minus beta xt minus 1. Let me just copy this one out. And we have the error over here, of course. Here I can replicate. It should be the same. And likewise with y. Okay. This is alpha 2. We're going to delve in a little bit more into what this beta means later on. But for pairs trading strategy, what that beta means is that is the hedge ratio in between the two assets. Okay. There is another important thing about the Granger representation is that this yt minus beta xt minus 1, this one should be I0. Okay? So this is a co-integrated relationship. Co-integrated or co-integrating relationship. Hey guys, it's late, I know. The co-integrated relationship. Okay, so far so good. Which one is I1? Which one is the other one? Oh, this is wrong. This is Y and this is X. This one, this is just the equation. But yeah, YT is definitely and 100% Y I1, and XT is should be I1 as well, because that's our starting point, right? Delta. No, delta should be I0. Remember, the X and Y should be I1, and the difference should be I0. Because it's I1. If you difference something that's I1, you get to an I0. Okay. Yeah. So also we can say that the co-integration relationship, the extent on that, let me write this down, is also the extent that is equilibrium from a long run relationship. Okay, and another really important detail is that alpha, what is alpha? So look that alpha is a sensibility that your movement towards the long run relationship. Okay, so alpha is 1 the speed, and 2, direction of how the series corrects itself from the disequilibrium. Okay. Now, who can tell me why do we do cointegration when something like correlation exists? I know right now in your head you just said, duh, because it's different, but how is it different? Omar.
Yeah. At first, I'm gonna ask you later to repeat a little bit of what you have just did. I just got a little bit lost, but about what you asked. Um, I think that in this case, you're like finding another variable that is not a lack of your actual variable. Okay,
Uh-huh.
so this is another variable. This is like that could predict the behavior of your variables. Like Coca-Cola is can be predicted as by time series with its own lags, but also can be predicted by the stock price of Pepsi, as you said, right? So I'd say
Mm-hmm.
that that's one thing that Sarima and Arima and all that stuff they cannot do.
Uh-huh. What about correlation?
How's like what about correlation? Like what?
What I asked was, why do we do these things when something like correlation exists? Because definitely you can also say that Pepsi and Coca-Cola's prices correlated, right?
Yeah, oh yeah. Okay.
Why don't we just forecast the running correlation or something like that? And most of you probably just thought, yeah, forecasting correlation is also easier, right? Now the thing is they are different. Okay, most things that are co-integrated are correlated, but not everything that's correlated is also co-integrated. Okay, remember that to be co-integrated, one, your regular series has to be I1. Okay, and of course your differential series has to be I0, right? So in the summary, co-integration is an equilibrium relationship in between different time series. Okay, now individually those time series are not in equilibrium. Now in contrast, for example, the correlation, let's say Pearson's correlation, that's the usual correlation we use. A Pearson correlation just describes a linear relationship in between two variables. Okay? Now why is co-integration useful to us? Because it allows us to incorporate both short-term dynamics, so deviations from the equilibrium, those moments in disequilibrium that we just saw, and also long-run expectations. And those long-run expectations are basically our correction towards the equilibrium in the long term. Okay? Let me write this down. So co-integration. So let's say executive summary. There's nothing executive about usual executive summaries. I don't know why we call it like this. An executive summary is Co-integration is an equilibrium relationship between two time series or more, right? Between just time series. However, those are not that aren't individually in equilibrium. It is useful to us because it allows us to describe, to incorporate both short-term dynamics, so deviations from the equilibrium, from the equilibrium, and long-run patience corrections. And that is the general introduction, because that's not all our class. We have 1 hour to go, guys. To co-integration. Any questions so far? Sum up the whole process to understanding a little bit better. So we haven't actually applied these things. We've only introduced the topic so far. We're going to see it applied. Maybe that will help, Omar. Okay, yeah, awesome. So let's go back to quantitative finance, right? Because this is basically statistics so far. Let's go back to the pair trading strategy. And remember, I said that this class was going to be a whole lot of talking. And I hope you guys talk with me as well. So usually when we do this kind of strategies, we think either pairs trading or mean reversion as well. So the idea of a mean reverting pairs trade is that you have two assets, okay? Two assets that generally have a sharing underlying factors that affect their movement. So, for example, Pepsi and Coca-Cola, a lot of people use McDonald's and Burger King. However, that's prior. So that's a little bit of trivia, on financial trivia. The stock for Burger King doesn't only include Burger King. They had a merger with Tim Hortons. So now, if you try to do a purse trading strategy right now, it doesn't work because you have a whole different kind of restaurant topic in between. So my was on Burger King before. Let's say Johnson and Johnson's under competition. United Airlines with American Airlines or Delta. Okay, you have a whole lot of ideas and some other relationships that are not that apparent. Okay, so what is the rationale for doing this? Is that their long-term share prices are likely to be in equilibrium due to the broad market factors affecting, say, for example, the airline industry, the hamburger industry, the dark soda industry for Pepsi and Coca-Cola. Okay, so imagine, for example, you have one factor that's affecting the production and consumption. So, for example, COVID. No, that's nothing for COVID because that's not systematic. That's systemic. Let's go back to McDonald's and Burger King. Okay, McDonald's and Burger King. Let's say that there's a supply chain disruption that only affects McDonald's. It doesn't affect Burger King. Okay. Now, that will lead to a temporary dislocation in their prices, right? So in this case, it would be a short-term dynamic that will generate a deviation in the equilibrium. Now, what do? So you do a long-short trade in order to profit from the disruption, and in time, the two stocks should return to their regular equilibrium value once the supply chain disruption that we put in is resolved. And that is basically the essence of pair trading. So in quantitative finance, what we are interested is carrying out this mean reversion strategies trading, but not only in one pair of trade, or one pair of, not only one pair of stocks, one pair of assets, right? But in a basket or in a portfolio of a lot of pairs, okay? And this requires a really robust mathematical framework, right? One, so and this is the hardest part, right? To actually identify what are the pair or basket of assets that pair together in order to have a mean reverting relationship. Okay. Now another idea is, for example, what we usually, or the most basic idea of co-integration, which is what we explained 20 minutes ago, that you that the pair is a non-stationary time series, okay, just like we did over here, so that you can form a linear relationship in between the two assets, such as they have a stationary combined series, which one has a fixed mean and variance, right? Now, the stationary time series might have short-term disruptions, like, for example, what we said about McDonald's supply chain, where the value wanders from the mean. Okay, remember that the combined time series is a stationary time series, so it should revert to that, to set mean. Now, the trading strategies can make use of this by going long or going short on one part of the pair and doing the other strategy on the other part of the pair at the appropriate disruption point and betting on a longer term reversion mean. Okay. Now, how does this usually work? So usually, mean reverting strategies permit you a wide range of instruments. And for example, one group did this for their final project last semester. What they did is they basically took several ETFs and they checked their pairs trading potential. So we had like 14, 16 different ETFs, and they checked their pairs trading potential. They simulated and modeled all of them and created a trading strategy based on the short-term disruptions that these individual pairs might have. Okay. Now, another a little bit more sophisticated approach to this is creating synthetic stationary time series by doing synthetic assets with the individual stocks or ETFs. Okay. Now we're going to see an example of this by looking at OTC instruments, such as, for example, let's say uh, a certain type of fuel price that's not really traded on the open market. Okay. So let's go back to what we can do. Okay. So a really important topic inside of this is unit root tests. Okay. this one. Unit root test. Now, what does a unit root test tell us? Anyone know? You should have already seen unit root tests with Jesus. So remember when we were talking about if a series is invariable? If a series is invariable, in order to find that the series was invariable, we had to take the roots of the model, right? Now, if that root, if we had an AR1, for example, we had just one root, right? If that root was less than 1, then the series was invariable. Now, if that root is equal to 1, first of all, it means that the model is not stationary. Okay? Because for a model to be invariable, it has to be stationary. And that means that you have a random walk. Okay? Now, some tests that we usually use are, the most used is the ADF or augmented computer. Another one is the Phillips Peron. And another one, not really used that much, but it exists, is a Phillips Solaris. Solaris. Yes. Now, all of these have different assumptions, but ultimately they are testing the same thing, that your root of the model, or the root in general, if you have more than an AR1, if you have an ARP or an ARIMA PQ, etc., that's more than 1, if the root is really not 1. Okay? So let's go. Let's describe the use of these, but let's not look at the equations, because you probably look at this with Jesus. Let's go into an example. Okay, so how should we start? Okay, let's make up a random walk. Okay, let's say that we have to define a random walk. You have z, ct is equal to zt minus 1 plus your error. Okay, let's say that your error is what? Omega. Yeah. Now, this process is clearly an AR1 process. However, your coefficient is 1. So you definitely have a unit root. Okay? Now imagine omega is a white noise and it's all good. Okay? Now with this random walk, let's create two more series. Create xt that, say, let's give it a coefficient p that multiplies our random walk plus another kind of error. Okay, let's say just put omega sub x. And the same thing for a series y. But with a different coefficient. Let's say it's cube. And this is y. Then we're going to make up a linear combination. We're going to make up a combination that is, let's put A, for example, AXT plus BYT. Okay, can you guys see where I'm going? If we have a random walk and two series that might be I1, by doing a linear combination of them, they might be I0 if they are co-integrated, right? Now, what are the values of this? Easy, right? We just put A times this. We just replace right? A times this plus B is the other series. We can also expand it further. We can say that let's pair together the C and the error terms. Okay, so this is AP plus what is it? BQ ZT plus the error terms together. Let me grab this one. The error from X, the error from Y, just together. And I forgot the letters. So this is A and this is B. Okay. Now, who can tell me if this series is stationary or not? Okay, let me rephrase that. How can this series be stationary? More simple than that. Force it to be stationary. Yep, that's it, Nicholas. So, what happens if where is it? Here. AB plus PQ equals 0. And our series is pure, just the error part, right? Exactly. So suppose that, for example, let's put some numbers to this. Say that P equals 0.3, Q 0.6, and after just some, if you want this with these numbers to have this relationship, then what do you need? You need A to be 2 and B to be, what is it, -1. So if P is 0.3 and Q is 0.6, no, you won't have to do these calculations. Don't worry. It's just making up an example. Usually you have to estimate this kind of stuff. with these two data points, in order to reach a stationary series combination, A and B have to be like this. And why do A and B matter? Because they allow us to estimate the individual time series. The combination of the time series, I mean. Oh, okay. That will be later on. Hopefully we'll reach that part today. I'm not sure. So, so what does that mean? It means that x and y are co-integrated when a is equal to 2 and b is equal to -1 if p and q have these values. Okay. Now let's not do it just theoretically. Let's just simulate something. Okay. Let's simulation. Okay, let's set a seed. Remember, for your results to be reproducible, you have to set a seed. Let's say that set is 1,000 values. Now let's go further. Let's say 185. Okay. And not only that, but we're going to fill it up in a loop in one towards length of z of I should be equals to the previous value. Remember our z model we created over here. So z minus 1. Sorry, I have to start at 2. Ci minus 1 plus, let's say that this error is normal. Okay, so R norm. Okay. We run this chunk. We have our z. We plot z. It should give me points, so I'm going to change the type to line. These are too many points to plot. Let's do 1,000. Okay. Looks like it's like a stock. Sure. It's a random walk, right? And if we run it again, it should give me the same result every single time. Why? Because I'm using a seed. Okay. Now let's look at the autocorrelation function of my series. Okay. Let's look at the ACF of the. Do you see something that you can model? Not really, right? Nothing. What about this? So you can clearly see that this is a random walk, and this is an I0, zero mean structure. Yeah, it's basically an ME1. No, not an ME1. Straight out the error. just a shock. It's white noise. Remember that this line is the line 0. If it was an ME1, you would have the line 1. Yeah. So the realization of Z clearly looks like a random walk. Just by looking at it, but we proved it. Okay. So we've created our white noise, right? Now we have to create our X and Y. Let's use the numbers from our example. So say that P is equal to 0.3 and Q is 0.6. Let's create X and Y. Now, first of all, we always try to fill our variables. So let me just pick X, Y, all of these together, 0. And X, we have the formula, right? X is P times Z plus an error. So X is P times Z plus, let me, simulations. This is a variable. Norm simulations. And then Y is very similar, but instead of P is Q. Right, now let's plot the different series. Y. Now, in order to make this pretty, I'm gonna use some packages, okay? Tidyverse. We'll maybe use tidyquant later. So let's create a data frame. X is X, Y is Y. And do I need something else? I should probably not, I probably don't need anything. No, I think I'm good. Okay. It works. About this. And this is free shape too. The name of these things. Let's see. Variable and value. Okay. I'm gonna plot it. ggplot. In data. Oh, so look at my data frame. Hold on. It has X and Y and all my values. Okay. Now if I do it with melt, it turns my data frame in a long format. Okay, so we have more rows. In this case, the same amount of columns. If we had more columns, we would have only 2 columns. So it turns my data frame in a long format. And you're going to see in a second why. So aesthetics, X is equal to X. Actually, I'm going to put another thing over here, which is called N. Which is called N. It should be 1, 2 simulations. Yep. I do not want to melt simulations. Let me check. What's the argument for melt on this kind of thing? It's called. I forget, but pretty sure there was a. Hold on. Yeah, there we go. ID variable. So ID variable is in text. I should not use n. I should use ID. Does it still work? It does. So X is actually the ID of my simulation. So ID. Y is value. And let's say color is variable. This is not like this. This is with a plus. Medium line. We should see both of them right now. Okay. Let's make it prettier. The themes. Just do theme. These are our two generated series. Okay. Scale, color. Maybe these ones. That's good. No, totally. Okay, let's just leave it at these two colors. Okay, where are we? Okay, we simulated our two different x and y's. Now, what do we do? What is our combination of the series? We said that with P 0.3 and Q 0.6, in order for our series to be stationary and to have a co-integration relationship, we need our combinations such as A is 2 and B is minus 1. Now, where do these fall into? We have to do 2x minus 1y. So the combination is 2x minus 1y. This. Let's check the structure. Okay, so comp the frame. We do a still. Doesn't. Data frame comp equals this. Comp. Okay. Let's just plot it. Okay. Bottom line. Aesthetics. X is equal to to y is equal to really does require, okay, let's just put one CMAS for simulations equals to one length of whatever I just put over there. X equal to 0. And this is our combination. Now, you remember x and y, right? We plotted x and y over here. X and y, do they look stationary to you? Nothing, right? What about our combination? Exactly, right? Just going to, in order to match the other one, the minimal, a little bit better. Okay, if we look at the ACF of our combination, if we look at the ACF of the combination, it's almost white noise. But it's very clearly stationary. Okay. Now, let's apply one of the tests. Let's apply the ADF. Okay, this is the moment that Gonzalo has to Google which of the packages has this function. I remember the name of the function is adf.test, but which package I have to load for that? Is it ATSA? It's T-series, I think. Yes, it's T-series. Sure. No problem. So T-series. There we go. So if we do the ADF test, which is the augmented leaky fueler test, to the to our combined um series, then we get a p-value that is 0.01. So our p-value is really small. So what do? We reject p-value small. So we reject the null. And what is the null? The null is that the series possesses a unit group. Okay. That is one test. Let's do a Phillips-Perron test. Phillips-Perron test gives us also 0.01, which once again yields us to the same hypothesis. We reject that we possess a unique root. Once again, there was another test that was the Phillips-Solari test. Phillips-Solari series as well. There we go. Phillips-Solari's test on our combinative value. A matrix. Do we have to make it a matrix? I guess we do. Oh, okay. So the Phillips-Solari's test we don't use on the combinated series. We used on the two individual series. We have to put it as a matrix. Okay, so let's combine the formula basically. This is one series. This is the other one. That easy, right? Okay, our p-value is smaller than the printed value, so our p-value is really small. What does that mean? It means that we reject the null, and thus our series does not possess a unit root. So, as Omar said, it cannot be more stationary. So, again, what does that mean in this context? It means that it's clear that we are dealing with a pair of series that are co-integrated. Now, imagine instead that, remember, we calculated this such as it would be co-integrated. Let's do the other way around. Let's do not this combination, let's do a bad combination. A bad combination could be, for example, the opposite. So minus 1x plus 2y. And let's run the one. Let's see how it looks. Bad combination. I didn't run this one. It doesn't really look stationary, right? Now let's run the tests. Let's do the ACF of the bad combination. So the ACF of the difference of the bad combination. This looks very unit rooty to me. Let's run the advanced Dickey-Fuller, the augmented Dickey-Fuller test. It's from T-series. Bad combination. So look at this thing. Before we had a before we had a p-value that was smaller than 0.01. This one is greater than 0.1, which means that at the 90th percentile, we fail to reject the null, which means that we have a unit root. P-value not small enough, we fail to reject the null. Remember that in statistics, you can never accept something. You either reject or fail to reject. You fail to reject the null, series has unit root. Or you cannot deny that the series has to, it's just wording, right? But we tested a bad combination and it's really just the combination that we had reversed. So not everything always works. Okay? So this is an incorrect linear combination, and thus this bad combination is not a co-integrated series. Okay? Okay, so far, guys, any question? I want to know if we have time to get into. I think we have to leave this for the Saturday. So what we're going to see on Saturday is how this applies to finding the. No, there's no interpretation for that plot. It's very unit rooty. That's all you need to know. What we're going to do on Saturday is, remember, we found these two equations, and we've also tested this equation. What we haven't done is looking into the error correction mechanism and finding this alpha, which noted the speed and the direction of the correction, and the beta, which we named as a hedge radio. Okay, we're going to see these things on Saturday, and hopefully you guys, with this introduction, will have a quite large and robust base for your class tomorrow with Jesus. Okay, and let's cut it at that. I will of course upload this script, and we'll continue 2 days from now. Right? So that's it, guys. Any questions?
Do you have to get another package in order to get those tests? The Explorer and all the other
So
ones?
T-Series is a package that comes with R. You don't have to install it, as far as I know.
Okay. Okay. Thanks.
I think T-Series also has a version of Let me test. T-Series test. Yeah, and yeah, it gives us the same result. But yeah, if you guys don't have any further questions, then that's it. I'll see you guys in 2 days. Good luck tomorrow. Ask Jesus every single doubt that you have for this topic, so we get to trading strategies. Okay? Very well, guys. Have a good one. See ya. Best of luck.